So, welcome once again to our online tutorial video. So today we're going to be talking about Laplace transform. So we're going to be talking about Laplace transform. Laplace transform. So you should just stay tuned to this video and be focused, but this is for advanced mathematics, right? It's not for O level or A level mathematics. So what is Laplace transform? What is it used for? You're going to be learning everything in the course of this video. You're going to be learning Laplace transform at its regard engineering analysis, right? So you're going to be using Laplace transform to transform variables or function from the time domain to the frequency domain, the time domain to the frequency domain. So basically, it's very simple and straightforward, but you have to need some particular good knowledge of mathematics, which may include partial fraction and some other kind of functions, right? So the inventor or the founder of this particular concept of mathematics is accredited to Laplace, right? Simon, right? He gave us this particular invention. He's a French mathematician, astronomer, and also a statistician, right? So Laplacian equation for electricity, which you can always get as partial square P of x, y upon partial x squared. So you need to know a prior knowledge of differential, partial differential. So we also have, when you differentiate this particular P of x with respect to y twice is equal to 0. If it is equal to 0, now P of x is temperature for thermal potential or electric charge in electrostatics. We also have the Laplacian differential operator, right? The Laplacian differential operator. Now, this you can see it as x. You are differentiating with respect to x. You're also differentiating partially with respect to y twice. Then you're differentiating partially with respect to z. So if you do this, this is called the Laplacian differential operator, right? Laplacian differential operator. Now, quickly, let's just jump into the main business of today. The Laplacian transform, it helps us transform variable, right? Such as x or y or z, which are the space variable, right? Or time t, which is a time variable. And then this can take you to another parameter s, right? The parameter right now, let's just be using s because it's more common in so many textbooks. Now, this particular s is now a variable. So mathematically, you can now say that Laplace, this Laplace you're seeing, it takes a function from where space or time variable to the frequency domain. For instance, if we're talking about time, it's always, if this is time, right, it's always positive. Do you get this? And time goes to infinity. You can't stop time, right? So is another way to just get the idea of what we're going to be discussing. So the Laplace is taken more frequently from the time domain, right? Now we're taking this to the frequency domain. Now you're integrating from 0 to infinity. Why 0 to infinity? Remember, time cannot be negative and cannot be stopped. Now, infinity, if you have not done anything about infinity or you don't know anything about infinity, just take infinity right now as a relatively very big number. The number that you can imagine. For me, it should be Googleplex or something of that nature. Good. Now, Google is a number. Googleplex is actually Google raised to power some kind of numbers, very large number. But for a child, it's relative, right? His infinity can just be 100, right? Counting from 1 to 100. For you listening to this video, probably your infinity may be somehow within quintillion. Then your relative is just a relative term, just a very big number. Now you're integrating from 0 to infinity, STF of t dt. Now the result should be just a function of this parameter s over here, right? So this becomes the Laplacian transform. So quickly, for a layman, Laplace transform is used to transform a variable in a function into a parameter, right? Straightforward. Now, a parameter is a constant under certain condition. Now, this video is live, is on demand. That's why I'm doing it for everybody to get it here. But you have to listen properly. So for the noise, you just do away with the noise and do away with the background. Don't let anything distract you. Now, clearly you can see that there is some certain conditions, some specific condition for this Laplace transform is that you must be integrating from 0 to infinity, right? 0 to infinity. So we're talking about 0 should be less than or equal to the time you're talking about, which is actually less than infinity. Now, any variable that does not vary within this range cannot be transformed. Cannot be transformed because time variable t is the most common variable that varies from 0 to infinity. Yeah, we know that it can never be 0 and it is going all the way to infinity. Time is always time, is always going to be there. Now, Laplace transform is a variable too in solving differential equation, for example, electronic circuit equation, and in feedback control, for example, in stability and control of aircraft system, you can use Laplace transform. You can actually use Laplace transform of this nature to do many other kind of transform. So quickly, I'm going to be discussing the examples over here. Now, this example, I'm going to pick the exponential one first to just get it done. For example, if you have a function of time, which is exponential, let's say a variable a t. Now, with the constant that a is a constant, right? So we're going to be treating the variable a as a constant, and the fact that 0 is less than or equal to t, which is less than infinity. This is the function we want to transform this using Laplace transform. Now, let's do this one after the other. The function is going to be here, so we're going to be talking about the L of t of this function f of t. In our case, this is L of t. The function is what? Is exponential at. This is the function we're going to transform. So our t is from 0 to infinity. Now you have es of t, which is over here. Can you see? This is our general function, right? Over here. So every time we're going to be considering it, we want to get this particular part of this equation. So the function we're going to substitute our function here is EAT, right? Then we're going to be solving it as a function of what? The t. So anything we're going to get over here, if you're going to integrate this, everything, the solution here should be a parameter, and then we have successfully transformed that particular equation in Laplace transform. Now, quickly, how can I do this? You have to be familiar with integration, which I'm going to be putting in this particular channel subsequent week, differentiation and integration. But this is very simple from your simple indices. You can add the powers, right? You can add this power. So I can have the integral over here. Now I'm dealing with only this part. This is the part you are supposed to solve the integral, right? This is the part you're supposed to solve. So this integral, I can put them together. I will now have exponential minus s of t. I'm going to be adding it with what? A of t, that this is the t. Now I'm going to be simplifying these powers. If I simplify these powers, I can do something like, say I have, I can put out minus s here plus a, then I can factor t out, right? This is t over here can be factored out. Exponential, t is factored out. That's why you're not seeing that t over here. Now, this is still a function of the t. From our integration, if I integrate this particular expression over here, excuse me, what I'm going to do here is very simple, right? I'm going to divide this by 1. So I have 1 upon that particular function that is beside the t. Now remember, it's only when you're dealing with exponential function, because when you integrate an exponential function, you actually get that function back, and then everything here, you're going to be dividing the denominator, right? Then I'm going to be having the multiple of this guy, which is exponential minus st minus s plus a, right? So if I have s plus a, right now, I have differentiated that particular function. Then all I'm going to do now is that, this function is of t, right? Is of t. But I'm going to be evaluating this function at 2 points because I've taken the integral. This is the integral. But I'm going to be evaluating this function at 0 and at infinity, right? At 0 and at infinity. I'm going to substitute infinity first into this expression. Then I would minus the particular expression when I substitute 0. So in fact, let me do it step by step. So first of all, in the whole of this function, I'm going to put infinity. Let me write it out. So I have 1 upon minus s plus a exponential minus s plus a. Then instead of t, I'm going to substitute infinity, right? I'm going to substitute infinity over here. Now, minus, I'm going to substitute 0 for t in the whole of this expression again. So I have, this is minus 1 upon s plus a, which is this expression over here, multiplying exponential, and I have minus, I have s plus a of t. Instead of t, I'm going to substitute what? 0. That's the only difference we have, right? So this particular expression over here, it covers the fact that you are substituting these boundaries. Now, anything exponential infinity here is 0, right? Everything here, because the exponential function, you're going to get 0. So this is 0, right? Now I have negative here. I have negative here. So negative multiplying negative, I'm going to have plus. That's plus, right? Now, 0 multiplied by anything over here is still going to be 0, right? 0 multiplying everything here is going to be 0. So here I'll be left with 1 all over s plus a exponential 0. Now, remember from your indices, anything raised to power 0 is equal to what? 1. If you're talking about 1 million raised to power 0, since it's raised to power 0, the answer is going to be 1. So that is why I'm going to be having 0 plus 1 all over s plus a. So we have 1 all over s plus what? Plus a, right? Because this particular exponent raised to power 0 is equal to 1. And that is why you have this as your answer. This particular expression as your answer, right? I think we made a little bit of error because this was actually in the denominator, right? This is in the denominator over here, right? So I can take out this particular guy. This is actually in the denominator over here. So sorry about that. We have 0 in the denominator. So this is actually supposed to be here, over here. So if it is over here, right? So I'm going to be having everything here multiplied by a negative sign. So I'm going to be having minus here, right? I'm going to be having minus here. But this minus that is outside, so it's going to turn this to positive, but this particular guy is going to be turning into a negative, right? Let's do it all over again so that you get what I'm trying to say. Right here, you have positive, but what we are saying is that you have this place is negative instead of here. So this place is actually supposed to be negative, right? It's only s that is negative, not s plus a. So you have to be careful about that. So you now have 1 all over. This negative here is going to be multiplying this one. You have s. Why this negative is going to multiplying this one, and you have minus a. So this is actually the particular result you're going to be getting. Right? So clearly, S, at no point should S be equal to A in the denominator. That's one condition here, because if A is equal to S, you're going to get 0 in the denominator, right? So this is particular transformation of this function from the time domain, right, to the frequency domain, right? Very clear. So here, please consider this as one parameter. This negative here is not for all of them, it's just for S, right? So that is why the minus that is here is going to multiply S and also going to multiply A. Why everything here is going to be equal to 1. For the fact that 0 multiplying everything here is 0, then exponential 0 is equal to 1. So you're going to be getting this. So final answer for this particular expression is very simple. So the answer here is just, you have your 1 over S minus A. How do we come about that? Let me go over it one more time. What you're supposed to do is to integrate. If you integrate exponential x, you're also going to get exponential x, right? But there is a variable here which you can check the table for integration. You will come to understand that if you integrate this particular function, you're going to be getting 1 all over this function, right? Then exponential that same function again. So what if I substitute the upper bound? This is the upper limit, right? Everything here, because of the infinity, is going to be 0. Everything here is going to be 0. But when I substitute 0, only this term here will be 0, right? And exponential 0 is equal to 1, right? Then that is why we have 1 all over minus S plus A. But there is a negative because the condition for integration says you should take the function when you substitute the upper minus the lower, and that is why you have negative here. So that's why your result is plus A minus A, while your S remain positive. So good luck with that. In the next video, I'm going to be doing more example and more advanced example. So stay tuned and watch for the next video. Thanks.